So as I said, we're going to start by talking about effective values for periodic signals. Please, my handwriting is worse than normal. So I'm going to ask you guys an odd question that is going to involve me drawing a very shitty picture. So what this is supposed to be is a standard receptacle here in the United States, where I think the longer thing is usually on the left-hand side. So this is just a very shitty drawing of an outlet. My question to you guys is, what voltage is provided by outlets here in the United States? 120, all right. Anybody have a different thing? All right, so let's go with Patrick's 120. He's not wrong. He's also technically not right, and that's what we're going to talk about here, okay? So Patrick, as you were foolish and volunteer an answer, I'm going to direct my question at you. Is that 120 volt a DC quantity or an AC quantity? DC. So you are suggesting then that the outlets in this classroom are giving out DC voltage. Okay, that's very incorrect. So power in practically every industrialized country in the world is distributed using AC voltages and currents, okay? So when you see those large transmission lines when you're driving, let's say from here to Mississippi or something like that, those big towers and all that kind of jazz, that's actually like 145,000 volts AC and all that kind of stuff. It gets stepped down to around 13,500 volts AC at distribution substations, and then transformers are used to step it down even further for home systems and all of that kind of stuff. Now, the magnitude of the AC voltage is not 120 volts. So this is where I'm getting into that thing where Patrick was both incorrect and correct at the same time, right? So let me put some things on here really quickly. So this bottommost terminal or receptacle is tied to ground. The large blade thing right here is actually the negative polarity terminal. And over here on the other side, really this wire is usually white, but white's not going to show up, so I'm going to use gray. Would be our positive polarity terminal, right? So if you were to ever work on rewiring an outlet, something like that in your home, which I've had to do multiple times because my home is quite old, you're going to be dealing, if your house is wired correctly, up to modern codes, with a ground conductor, what's called a neutral conductor, and then what's called a hot conductor. And there is some time varying voltage that you'll see between the hot conductor and the neutral conductor. The neutral and ground are usually tied together at your load center, commonly called the breaker panel, and all that kind of stuff. Doesn't have anything really doing with what we're talking about today.
They asked me which hole of a plug is the hot, and I guess the long one.
You're incorrect.
Also,
Yeah. Nope. I thought because the student asked, and it is actually the smaller one is the hot, the longer one is the neutral. Anywho, so we have some time varying voltage, and that voltage is approximately, let me put this here, 170, really it's like 169.7 and some change. Cosine, 120 pi t plus some phase angle theta v volts. Okay. The 120 pi comes from the fact that here in the States, we use a 60 hertz excitation frequency in all of our standard AC systems. And 60 hertz multiplied by 2 pi gives us an angular frequency of 120 pi radians per second. Okay. Now, we commonly refer to this as 120 volts RMS, where this 120 volts RMS is what's known as the effective value for that time varying voltage waveform. So that's why I said Patrick wasn't fully incorrect, right? We commonly call the voltage that's coming out of our receptacles 120 volts, but that's really just an electrically equivalent quantity that we use to do math because it makes things easier, right? Doing a bunch of math on that time varying voltage would be wildly annoying, so we just don't do it. So now let's talk about what an effective value actually is, okay? So an effective value is a DC equivalent value that delivers the same amount of average power as the periodic signal. So what this means is that if we were to connect a voltage source, a sinusoidal voltage source having approximately 170 cosine 120 pi t plus some phase angle theta v volts to some load, and we were to measure the average power drawn by that load, it would be effectively the same thing as if we'd replace that voltage source with a 100-volt DC source, okay? So that's all an effective value is it's just kind of a DC equivalent representation. So let's figure out what the relationship between these two numbers is, okay? So let's say that I'm dealing with a simple resistive load, okay? So the average power delivered to a resistive load is going to be 1 over the period times the integral over 1 period of the time varying voltage squared divided by the resistance value in terms of a voltage waveform. And pretty similarly, it's going to look like 1 over t times the integral from 0 to t of I squared as a function of time times R dt for a periodic current waveform, right? So V squared over R, I squared times R, relationships that we're well aware of previously. What we're going to do now, so this is what our average power would be for a periodic voltage signal or a periodic current signal. Now we're going to talk about what the average power would be for a DC signal. So for a DC voltage signal, our average power is just going to be the DC voltage squared divided by the resistor value. It's just a relationship that we came up with on the 3rd day of class, I think. And similarly, for a current, we're just going to have our DC current squared times our resistor value. So in order for us to figure out the relationship between our time varying voltage or current and our effective DC voltage or current, I'm simply going to equate those two relationships for average power and then algebraically manipulate things, right? So let's look at the voltage equation first. So I have VDC squared divided by R is going to be equal to 1 over T times the integral from 0 to T of V of T squared over R times dt. Well, right from the jump, I can see that there's a common factor of 1 over R on both sides of the equal sign. So it turns out that the resistor value doesn't even matter. There's just going to be a direct relationship between the DC voltage and the periodic AC voltage. So now on the left-hand side, I have the DC voltage squared. So to get rid of that square, I'm just going to take the square root of both sides, right? So that's going to give me the following relationship. VDC, which I'm now going to call V effective, which is the DC equivalent, is simply going to be the square root of 1 over T times the integral from 0 to T of the square of our periodic voltage waveform. And the units of an effective value for voltage is given as volts RMS. So that subscript RMS lets us know we're dealing with an effective value so that we can distinguish between volts for our periodic signal and volts for our effective value. So let's talk about where this RMS thing comes from. RMS stands for root mean squared. It is literally just telling us the mathematical operations we are doing to get the effective value. We are taking the square root, that's the R, of the arithmetic mean, that's just a fancy word for average value of the square S of the waveform in question. So literally the units RMS tell us what mathematical operations to do to our periodic voltage signal in order to get an effective value. We could do an incredibly similar derivation and find that the effective value for a current is going to wind up being the exact same thing. Where a current effective value is measured in amps RMS. Now, normally I would go through a couple of quick examples illustrating how to use this expression to determine the effective value for some interesting waveforms like square waves, triangular waves, and all of that kind of good stuff. But because I'm trying to make this portion of the class a little shorter so that we can spend more time talking about the difficult material, we're just going to look at the effective value of a sinusoidal signal, okay? Because that's what we're principally interested in. So let's say that I have a voltage of the form Vm cosine omega t plus some phase angle theta v of this voltage waveform would be, right? So I'm simply going to apply my equation. So V effective is going to be the square root of 1 over T times the integral from 0 to T of this voltage waveform squared. And I'm going to use that same trig identity that I used last Friday. And that's going to make this come out to be 1/2 Vm squared plus 1/2 Vm squared cosine twice omega t plus, excuse me, this should be twice theta v dt. Bless you. Now, one thing that I'm going to need to do is I'm going to need to figure out the period of my periodic voltage waveform and how it relates to my angular frequency omega, which we've technically already done, right? Back when we were doing our review of sinusoidal signals, we found that, let me do this in blue over here on the right-hand side. We know that our linear frequency f is 1 over our period. We know that omega is 2 pi f. And so putting these relationships together, we can see that t is just 2 pi over omega. Let me double check and make sure it's not omega over 2. No, omega over 2 pi would just be f. Yeah, 2 pi over omega. So all I'm going to do here really quickly is just replace this 1 over t with omega over 2 pi and replace this t with 2 pi over omega. And now I'm in a good place to do things. Right? So I'm going to split my integral up into 2 parts effectively. So I'm going to have the integral from 0 to 2 pi over omega of 1/2 Vm squared dt. And then I'm going to have the integral from 0 to 2 pi over omega of 1/2 Vm squared cosine twice omega t plus twice this integral right here should look kind of familiarish, right? We were doing something similar to this last Friday when we were looking at a mathematical definition for our average power. We just didn't have the square root sign over things, okay? So effectively, what this integral right here represents is us integrating this sinusoidally varying function over exactly 2 cycles, okay? And I say it's over exactly 2 cycles because our period is defined for an angular frequency of omega, but this AC bit right here is oscillating at twice omega. So it's oscillating twice as fast, which means we're integrating over exactly 2 periods. So what is the integral of any sinusoidal function over an integer number of periods? 0. We showed this graphically last Friday, which means this whole big ugly term right here just goes to 0. So all we have to worry about is that first bit. Well, 1/2 and Vm squared are literally just constants. So we can pull them out of the integral. And so that's going to give us the square root of omega over 2 pi times 1/2 Vm squared times the integral from 0 to 2 pi over omega dt. What's the integral from 0 to 2 pi over omega, from 0 to 2 pi over omega of dt? 2 pi over omega. So we're going to have 2 pi over omega multiplied by omega over 2 pi. Those guys cancel each other out. And what we're left with is Vm divided by the square root of 2. What's 170 over square root of 2? Pretty close to 120. Yeah, and that 170 is the bit that's a little rounding errored off. Okay? So what this tells us is actually something incredibly interesting. Okay, may seem boring. It's just whatever the magnitude is divided by the square root of 2. But notice that this result in no way, shape, or form depends on omega, our angular frequency, and in no way, shape, or form does it depend on theta v, our phase angle of our periodic sinusoidal signal. So anytime we have a sinusoidal signal, the effective value is just going to be the magnitude divided by the square root of 2. Why that's super great is because here in the States, we work on a frequency of 60 hertz. In Europe, it's 50 hertz. Two different omegas, but effective values get rid of that, right? So it does not matter where you are in the world, analysis done using effective values is going to be consistent regardless of what your excitation frequency for your system is. So let's take a look at something. In our last class meeting, we found that for a sinusoidally excited system, our average power was given by 1/2 Vm times Im times the cosine of theta v minus theta I. I'm going to play around with that factor of 1/2 out front, and I'm going to distribute it like so. So I would have Vm over the square root of 2 times Im over the square root of 2 times the cosine of theta v minus theta I, which is the exact same thing as our effective voltage times our effective current times cosine theta v minus theta I. So using effective values gets rid of that pesky factor of 1/2 that came about just because of the trig identity that we were using. Somebody much, much smarter than me noticed that this is technically the real part of a complex number. Okay. So now let's talk about complex power. So before we get into our mathematical relationships, I'm going to introduce a new domain that we are going to be doing circuit analysis in, okay? So if we have a signal like this, V of t is equal to Vm cosine theta v, we know that this is the time domain representation of our signal. And we have been using a frequency domain or a phasor representation as follows. So phasor voltage V is just Vm angle theta v. This is our frequency domain representation. And now we're going to introduce the RMS phasor domain. RMS phasor domain is where we do all of our complex power calculations, okay? And this is going to be a difficult transition, and that is meant extremely sarcastic. Okay. So our RMS phasor voltage, sorry, my screen is jumping around. I'm going to denote it with a tilde over the top as opposed to just that flat bar. This is nothing more than our phasor voltage V divided by the square root of 2, which would look like Vm over root 2 with an angle of theta v, or simply V effective with an angle of theta v. So to go from the frequency domain into the RMS phasor domain, all we're going to do is just divide the magnitude of our phasor by square root of 2, and we're good to go. Phase angle does not change literally at all. So with this understanding, an RMS phasor current would be something like I effective angle theta I. So if we look back at our average power relationship, where we have P average is equal to V effective times I effective times the cosine of theta V minus theta I, this is just the real part of the following mathematical operation. My RMS phasor voltage V multiplied by we call this quantity complex power. So complex power is literally just a mathematical construct that electrical engineers created to help us understand what different parts of the system is doing in a steady state sinusoidal case. Okay. So our complex power is the product of two complex numbers. And so therefore it is going to be a complex number itself. Okay. So let me hit you guys with some equations here. So S with a bar over it is our complex power. Before we move along from this point, let's talk about units. This is 100% a trick question. What should the units of complex power be? It looks like it should be, but it isn't. And it isn't because electrical engineers just made up a unit so that we can tell the difference between complex power and average power, which is measured in watts. Because engineers are so lazy and boring, we made up the unit of the volt ampere. That is the unit of complex power. So instead of saying a volt times an amp is a watt, we now say a volt times an amp is a volt amp when we're dealing with a complex power system. So here is our unit, the volt ampere. Okay. So in order to calculate our complex power, we simply need the RMS phasor voltage drop across our element of interest, the RMS phasor current across our element of interest, and then we conjugate the current in that multiplication. Okay. Now, like I said, this is inherently a complex number, which means we can represent it in a rectangular form or a polar form. So let's deal with the rectangular form first. Yes?
Make sure you conjugate the current, but not supposed to multiply that.
Correct. So that is the voltage multiplied by the conjugate of the current. If I were conjugating both of them, I would put V and I in parentheses to indicate that both were being conjugated. And we'll work some examples. All right, so we're going to start with our rectangular form definition or expression here. So we're going to have the magnitude. So that's going to be V effective, I effective, cosine theta V minus theta I plus J V effective, I effective, sine theta V minus theta I. This part right here is the average power. We already know that. We came up with this definition a few minutes ago, right? So this is our average power. Typically given the symbol P or P with a subscript AVG, let us know that it's average power. Okay. I'm just going to call it capital P right here. The units of average power are watts, which is what we've been dealing with up to this point. Okay. So let's talk about what the average power represents briefly. Okay. So the average power represents the portion of the complex power that is capable of performing work. It's associated with real loads or the resistive portion of loads. So effectively, the average power is just the part of the complex power that gets converted to heat. That's all the average power is. The part over here on the right is what's called the reactive power. Commonly given the symbol Q. So this is the imaginary part of our complex power, but it has a very non-imaginary purpose. I'm asking because you work in this industry, if I say anything out of turn, please correct me. What the reactive power represents is temporary energy storage in our system. So we only have reactive power whenever there are capacitors and inductors in our system. Okay? So when we were looking at the instantaneous values for our power last class meeting, we saw that the average value of the instantaneous power absorbed by a capacitor or an inductor was 0, which means exactly half of the time those elements were absorbing power, and exactly half of the time those elements were supplying power back to the source. So they are inherently temporary energy storage. They're constantly taking energy in and releasing it back out. Okay? This is an integral part of how our grid functions. So without any reactive power in our electricity grid, we would actually have constant blackouts and stuff like that every time a large group of people turned on appliances at the same time. So effectively, because most people come home and cook dinner at roughly the same time, everybody turning on their ovens or their microwaves all at once would cause a nationwide blackout. But because we have temporary energy storage in the form of inductors and capacitors in our system, that literally doesn't happen, right? So the reactive power helps us ride out variations in our supply voltages effectively. There are things called static VAR capacitor banks and all that kind of stuff that are used. So like, I'm gonna tip talk to Beyonce here a little bit, but it'll be okay. How many of you guys remember the Super Bowl about 10 years ago that was in New Orleans where Beyonce played the halftime show and power went out? Something like that, I think so, yes. A similar phenomenon happened in Great Britain when their team was doing very well in the World Cup several years back as well, I believe. Effectively, there came a point where after the game was over, everybody stopped, turned off their TVs and turned on their electric tea kettles at the same time and caused a blackout in the city of London. It's because that large change in the load on the system wasn't counterbalanced by enough reactive power. Similar thing happened in New Orleans. So without having reactive power banks in the form of large capacitors, we wind up having blackouts. Static VAR capacitors are a relatively new technology that are introduced within the last 10, 15 years by utility companies that protect very, very large scale manufacturing operations from ever experiencing a blackout. So I was talking to, this might have been people from Entercon actually, last year that were visiting the ICE students. And they were talking about having to protect Texas Instruments manufacturing capabilities from problems with the grid over in Texas. The issue being is that Texas Instruments is a semiconductor manufacturer. It literally cost them a couple of $1 million to get everything started back up. So they need very, very special protection from ever seeing the effects of a blackout because it will literally cost them millions and millions of dollars. So the utility companies in Texas just started using these huge capacitor banks to effectively store energy just for TI so that they never, ever face an outage. Okay. All right, so the units of reactive power, this is another made up unit. It's just volts times amps, but because it's reactive power, we call it a volt ampere reactive or a VAR. Okay. So we now have 3 different units for power banging around in our head. But the units tell us which parts of the complex power that we're looking at. Okay. So if we're looking at complex power, things are measured in volt amperes. If we're looking at a real part of complex power, the average power, we're talking about watts. And if we're looking at reactive power, we're going to be using VARs. So here's our rectangular form representation, which could be simplified to P plus JQ. In polar form, we're going to have the following results. So we have V effective times I effective with an angle of theta V minus theta I. V effective times I effective also has a special name. We call this the apparent power. No, I mean, Ashton's not wrong. Like literally, this is just a made up concept for electrical engineers to say, this part's doing this and this part's doing that. That's literally all it is. Okay. Apparent power typically has the symbol, the magnitude of S, our complex power, because that's literally all it is. Okay. So the apparent power is what's used in designing a system. I say that because it's kind of a worst case scenario representation. What I mean by that is it's just the product of the effect. There is no phase difference taken into account, which will actually make the parts of the power smaller. So this is realistically the largest possible power that your system will ever draw. And so you design to that so that you're able to withstand everything. Okay. I don't know how many of you guys have ever had to look into purchasing an uninterruptible power supply, or I don't know, maybe help the parents buy a generator for their house or something like that. But typically they have 2 different ratings. One rating is in volt amperes. That's the apparent power that's rated for. And the other rating is measured in watts, which is the average power that it's rated for. Typically, those 2 numbers are relatively close to each other. So you might see something that's rated for like 2,000 volt amperes and 1,800 watts, so that it can only support a small amount of reactive power in the system before it's receiving the ratings and all of that kind of good stuff. Okay. But anyway, this is what's used as a design criteria. So all of the National Electrical Code conductor sizing and all that kind of stuff is based on your apparent power draw. And then this angle over here also has a special name because everything has to in this convoluted thing. This is what's known. Oh, I already used red, so let me use orange. Sorry. As our power factor angle. And I'm going to give it a symbol of theta S. So we're going to go into a lot more detail about what the power factor angle means in a few minutes when we discuss power factor. But before I do that, let me write this out here. So instead of having this equation, we might just choose to represent it as the magnitude of S with an angle of theta S. So realistically here, buried inside this one operation, we have 4 different equations. I expect you guys to memorize none of them. Let me explain what I mean by that. If you can remember what each of these parts represent, as long as you can perform this operation, multiplying a voltage and a current, if you tell your calculator to output you have average power and reactive power. If you tell your calculator to output the result of that multiplication in polar form, you have apparent power and power factor angle. So there's really no need for you whatsoever to memorize all of these equations, because as long as you can do this, you have everything. So having these individual equations is completely and utterly pointless, in my opinion. I always just calculate complex power and then take the part that I need for whatever I'm doing. That's the approach I'm going to take. I'm not saying that you're wrong if you memorize all these equations. I'm saying you've wasted time. All of these different quantities can be related to each other through a handy graphical tool, which is called the power triangle. So in our power triangle, that is just a plot of our complex power on an imaginary plane, right? So we have our real axis over here, our imaginary axis on top. And so we might see something like this. We'll have some complex power S. The projection of S onto the real axis is our average power. The projection of S onto the imaginary axis is our reactive power. The length of this vector S is our apparent power. And the angle formed between S and the real axis is our power factor angle, giving us the exact relationships that I've defined above. S is equal to P plus JQ in rectangular form, or magnitude of S, angle theta S in polar. And the power triangle actually tells us quite a lot of information, right? So for example, with this guy right here, as it's currently depicted, whatever I'm calculating the complex power of is absorbing average power, and it is absorbing reactive power. So I can say that because both are positive quantities. So that tells me that this is an inductive load. It contains some resistance and some positive reactance, which is just inductance, right? If this were instead flipped down about the horizontal axis, this would be indicative of a capacitive load, because it is applying reactive power. Right? All right. So let's talk about alternative relationships that we can use before we move on to power factor. Okay. So all I'm going to be doing is manipulating these two equations, right? So first, my fundamental definition for complex power. And then this guy over here, V is equal to I times Z. What is that second equation? Ohm's law, that's it. Going back to very, very basic things here, okay? So I can use these two equations together to effectively express the complex power absorbed by anything only in terms of the voltage or only in terms of the current. So let's do things only in terms of the voltage first, right? So I would have S is equal to V. And now I'm going to rearrange Ohm's law to express I in terms of V. And so that's to me just going to look like V over Z. And because I need to conjugate my current, I'm going to conjugate this whole fraction. Okay. So this is going to look like V conjugate times V over Z conjugate. Because whenever I conjugate a ratio, I have to conjugate both the numerator and the denominator. So what's V conjugate times V? This is that identity that we talked about when we were looking at complex numbers the first time. Not just the real part. So let's look at this really quickly over here on the right in terms of a polar form complex number, okay? So let's say that I have a complex number A, that is the magnitude of A, angle theta A, to get B. So change the sign on the angle. Absolutely right. So magnitude of A, angle negative theta A. If I multiply those two together, A conjugate times A, that's going to look like the magnitude of A times the magnitude of A with an angle of theta A plus negative theta A. Well, theta A plus negative theta A is just 0. And the magnitude of A times the magnitude of A is just the magnitude of A squared. So whenever I multiply a complex number by its complex conjugate, I just get the magnitude squared. So that means this is just going to be V effective squared divided by Z conjugate. Works for any type of impedance that I have. As long as I know what it is, all I need to know is the magnitude of the voltage drop across it, and I can calculate the complex power. Don't even need to know the phase angle at all. Similarly, I can put things in terms of current, right? So I know that V is equal to I times Z. So I'm going to have I times Z times I conjugate, which is going to look like I conjugate times I times Z, or simply the effective value of the current squared times the impedance. And now I know my complex power for any impedance in terms of just the magnitude of the current flowing through it and the impedance value itself. Okay. So let's take these one step further and look at what happens if we have just a resistor, just a capacitor, or just an inductor, right? So the impedance of a resistor is just the resistor value itself, right? So that means the complex power is going to be V effective squared divided by R, or I effective squared times R. These are literally just our DC relationships for power for a resistor. Okay? We can see from this that our complex power is purely real. There is no imaginary part whatsoever, and it's always positive. So we can say definitively that resistors absorb average power. That is their role in a steady state sinusoidal circuit from a power perspective. Now let's look at an inductor. So the impedance of an inductor given by J omega L. So our complex power in terms of the voltage would be V effective squared divided by negative J omega L, because I need to conjugate my impedance. And what is 1 over negative J? Positive J in the numerator. Absolutely right. So that's just going to look like positive J times V effective squared over omega L. Let's do things in terms of current down here on the bottom. So we would have I effective squared times J omega L, just reorganizing that to put the J out front. That's going to look like J omega L times I effective squared. So what can we see that inductors do? Well, the complex power is purely imaginary. There is no real part at all, right? It's always positive and imaginary, which means inductors absorb reactive power. And lastly, we'll look at capacitors. So for a capacitor, our impedance is 1 over J omega C, or we could choose to represent that as negative J divided by omega C, which is what I'll do. Okay. So for a capacitor, in terms of the voltage, we are going to have V effective squared. And now I'm going to divide by the conjugate of the impedance, right? So since I'm dividing by ZC, that's going to look like omega C over negative J. But because I'm doing the conjugate of that, it's going to look like omega C over positive J. Well, 1 over J looks like negative J on the numerator. So this is going to give us negative J omega C times V effective squared. In terms of our current, we're going to have I effective squared times negative J over omega C, which is going to look like negative J times I effective squared over omega C. And now we can look at what's going on here, right? So for a capacitor, we can see that the complex power is purely imaginary, but this time it's always negative. So capacitors actually supply reactive power all the time. So these are the roles of the 3 different types of circuit elements that we'll have in our steady state sinusoidal circuits, right? So resistor's job is to absorb average power. Inductor's job is to absorb reactive power, and the capacitor's job is to supply reactive power. We're going to use all of those relationships when we talk about what's called power factor correction, which will be our last topic for this class. We're covering it on Wednesday. All right, so let's work an example of these relationships into use. And then after we do that, we'll talk about power factor. So let's say that I have the following circuit. So this is going to be a 120 angle 0 degrees volts RMS voltage source, which means we're already dealing with a circuit that is in the RMS phasor domain. So there's no need for us to convert from the frequency domain into the RMS phasor domain. I'm telling you that explicitly because you have homework assignments. Anytime they're asking you to do anything that's complex power related, you need to make sure that you're in the RMS phasor domain. And the best way to check is if you're given units of volts, you're not. If you're given units of volts RMS, you are. So if you don't see the RMS on the units, convert into the RMS phasor domain. All right. So here we have some impedance ZA. Here's some impedance ZB. Here's some impedance ZC. And then over here on the right-hand side, we have a current source, 5 angle 45 degrees amps RMS. And let's say that impedance ZA is 10 plus J8 ohms. Impedance ZB is 12 minus J3 ohms. And impedance ZC is 8 angle 30 degrees ohms. So what I want us to determine is the average power absorbed by impedance ZA, the apparent power absorbed by impedance ZB, and the reactive power absorbed ZC. We won't necessarily do them in this particular order. Those are just the three quantities that I am interested in. So, because this is our first time doing this, I'm going to kind of lead the discussion here. So, I'm going to identify the things that I might possibly need in order to figure things out, okay? So, I might possibly need the RMS phasor voltage drop across impedance ZA, the RMS phasor voltage drop across impedance ZB, and the RMS phasor voltage drop across impedance ZC, which I'm choosing to represent with positive polarity on the right instead of positive polarity on the left like the other ones. Should be kind of obvious why, based on the direction of the current, but anyway. So, those things, or I might need the RMS phasor current flowing through impedance ZA, the RMS phasor current flowing through impedance ZB, or the RMS phasor current flowing through impedance ZC, right? Because of our alternative relationships that we came up with a couple of minutes ago, realistically, we only need the voltage drop or the current through any of those impedances in order to calculate the complex power. And then once we know the complex power, we can pick and choose what piece we need in order to actually answer the question that was posed to us, okay? So, which thing do you guys want to solve for first? Yeah, QC is by far the easiest in this particular circuit, right? So, the complex power SC could be expressed as the magnitude of voltage VC squared over ZC conjugate, or the magnitude of current IC squared times ZC, using our alternative relationships. So, which one do we want to use? The second one, because I make it harder than it needs to be, okay? So, what's the magnitude of the current flowing through impedance ZC? 5 amps RMS. So 5 amps RMS squared times impedance ZC of 8 angle 30 degrees ohms. So 25 times 8 is going to be 200 angle 30 degrees volt amperes. So that is our polar form representation. I don't know what cosine of 30 degrees is off the top of my head, so I'm going to get a calculator. So 200 angle 30 expressed in rectangular form looks like 173.205 plus J 100 volt amperes. So we figured out what the complex power is. We're asked to find the reactive power. So what is it? What? So the 100 part is right, but it won't be VA because reactive power is measured in VARs. So it'll be 100 VAR. So it's just this number. And then we give it units of VARs because we're specifically looking for the reactive power. Right? All right. One down, two to go. So what do you guys think we should focus on next? So to me, it looks like I could solve for VB rather easily if I chose this bottommost node as ground and solved for this nodal voltage, which is the exact same thing as the voltage drop across impedance VB, right? So that's the path that I'm going to take. So I'm just going to apply KCL at that top middle node. So that's going to look like VB minus, let me put it over here, 120 angle 0 degrees volts RMS divided by ZB, which was 12 minus J3. Actually, that should be ZA there, 10 plus J8. Plus VB over ZB, 12 minus J3. And then I'm going to have minus 5 angle 45 degrees amps is equal to 0. So that's just KCL at that top middle node. And because I know the current that's flowing through ZC, I'm not going to bother figuring out the voltage and then dividing by the impedance to get the current because I've already got it, right? So just simple application of Kirchhoff's current law. So from here, I can rearrange things. So I would have VB times a factor of 1 over 10 plus J8 ohms plus 1 over 12 minus J3 ohms is equal to 120 angle 0 degrees volts over 10 plus J8 plus 5 angle 45 degrees. So throwing stuff in my calculator really quickly. 1 over 10 plus 8i plus 1 over 12 minus 3i. I'm going to store that in my calculator as x. 120 angle 0 over 10 plus 8i plus 5 angle 45. Store that in my calculator as y. And then y divided by x gives me 77.917 angle negative 0.238 degrees volts RMS. From here, the complex power absorbed by element B is just going to be the magnitude of VB squared over ZB conjugate, or 77.917 volts RMS squared divided by 12 plus J3 ohms. So let me throw that into my calculator. And I got 490.813 with an angle of negative 14.036 degrees volt ampere in polar form, and 476.158 minus J 119.039 volt ampere in rectangular form. Because I was asked to find the apparent power, scrolling up there to make sure, which is the number that I'm looking for. The magnitude, so 490.813. So this guy right here tells us that SC is 490.813 volt amperes. All right, so the last thing that we have to figure out is effectively the complex power absorbed by impedance. Yes. Should be B. Did I write? Yeah, definitely should be B. Thank you for that. So the last thing that we have to figure out is what's going on with impedance ZA. So how might we go about doing that? Recall that we know what VB is, and we know what IC is at this point. So we could do KVL around the left-hand loop to figure out VA, or we could do KCL at the top middle node to figure out IA. Either one of those will get us the answer that we're looking for. Let's do KVL, right? So VA looks like it's just going to be 120 angle 0 minus VB. So did I store that in my calculator? Heck yes, awesome. So 120 minus that, I get to be 42.085 with an angle of positive 0.441 degrees volts RMS. From here, SA is just the magnitude of VA squared over VA conjugate. So that's going to look like 42.085 volts RMS quantity squared over 10 minus J8 ohms. So the magnitude of T squared over 10 minus 8 pi, I get to be 138.304. Angle positive 38.660 degrees. And in rectangular form, that looks like 107.998 plus J 86.398 volt amperes. And I'm looking for average power. So which number is it? The real part, so 107.998. What are the units? Absolutely right. I want you guys to be aware, if you haven't looked at the practice exams and all of that kind of stuff, that I am absolutely enough of a dickhead to put on your exam. So if I ask you to calculate the reactive power, I will put the correct answer in VARs, the correct numerical answer in VARs, but I will also put the correct numerical answer in watts and the correct numerical answer in volt amperes, and I am expecting you to do the correct one. If you get the units wrong, you'll still get some partial credit, but you will not get it all the way right. Okay, just want to be really, really clear about that, being consistent with what I've done on every other test. Yeah. So you'll get 3 points effectively for getting the numerical answer right, but you'll only get the full 4.5 points if you get the unit correct as well. All right, so power factor. All right, so let's work with a mathematical definition first, and then let's talk about what it is, okay? So our power factor, PF, is defined to be the ratio of the average power to the apparent power in our system, which comes out to be nothing more than the cosine of our power factor angle. Okay? So what's the largest value that the power factor can ever have? What's the most negative value, I guess, that the power factor can ever have? -1. What's the smallest value that it can have? 0, okay? So effectively, the power factor is going to be a number between 1 and -1, or its magnitude is going to be between 1 and 0, okay? So realistically, we can kind of think of it as a type of efficiency in our system, right? Where if the power factor is a positive number, it's talking about the efficiency at which we're absorbing power. And if it's a negative number, it's the efficiency at which we are supplying power. Okay. So let's talk about what it physically represents now, okay? Average power, P, is what we as consumers of electricity pay for. That is what's on our bill. The average power multiplied by the time in the billing cycle is literally what we pay for on our utility bill, okay? So that's what we pay for. Apparent power, S, is a measure of what the electric utility has to produce. Okay? So this is just a ratio of the amount of power that we are billed for over the amount of power that they produce. So if our power factor is very small, the electric utility is losing money, okay? They don't want it to be a small number ever. So realistically, they're going to do whatever they can to keep it within some threshold, usually 97.5%, 95%, something along those lines. And if it ever falls below that, they're going to fine you. Now, as a household user, that's never going to be an issue. So many of the loads in our house effectively act as purely resistive loads. All of our lighting is a purely resistive load. All of our televisions, computers, and all of that kind of stuff are all resistive loads because there are voltage regulators and all of that kind of stuff that make all of those semiconductor devices just work off of DC. Okay. There are going to be a few inductive loads. So effectively anything that involves a motor is probably going to be an inductive load. So your oven, particularly if you have a convection oven, is going to have an inductive load because it's got fans that are blowing air around, and then it's an electric oven. It's going to have a large resistive load from the heating element. A washing machine is going to be more of a mid-range inductive load. So it's definitely going to draw some amount of average power for powering all of the electronics and all of that kind of stuff, but the agitator motor is going to look more inductive. Our dryer is going to be similar to our oven, large resistive load from the heating element, small inductive load from the motor, all that kind of good stuff. So realistically, in a home setting, our power factor is always going to be within the threshold that we don't pay a fine to the electric utility. However, large-scale industrial consumers, that will not be the case, right? So thinking about places that are going to have conveyor belts and things like that, lots of inductive motors used to move things from place to place, point to point within their system, they might operate at a power factor that is lower than the threshold, and so they might face a fine. What we're going to talk about on Wednesday is a topic called power factor correction, which is just a common technique used by industrial consumers to correct their power factor to a point where they're not receiving a fine. Okay. All right, so let's talk about what different power factors mean. Okay, so let me do this in the opposite direction. Okay, so let's say that theta S is equal to 0 degrees. So if theta S is equal to 0 degrees, then what is our power factor? 1, right? A power factor of 1 is typically called a unity power factor. And this occurs, obviously, whenever our apparent power and our average power are the same number, which is only ever possible if our load is purely real, right? So we need a pure resistive load for this to happen. So R is greater than 0, X is exactly equal to 0. Now let's say that 0 is less than theta S is less than 90 degrees. So effectively, we're talking about theta S having a positive value, okay? So in this case, our power factor will be between, so we can put it as 0 is less than our power factor is less than 1. And this is what's called a lagging power factor. Okay. So it's called a lagging power factor because our current is lagging our voltage. So what kind of system do we have if we know that the current is lagging our voltage? Either inductive or capacitive. So you got a 50-50 shot of getting it correct. Inductive, right? So This is R greater than 0 and X greater than 0, right? So our power factor can tell us what kind of load we have, or vice versa. If we know what kind of load we have, we know what our power factor should be, or at least what range it should be in. When theta S is equal to exactly 90 degrees, our power factor is 0. So we're operating at 0% efficiency because we don't have any average power being absorbed, okay? This only happens for a purely inductive load. Where R is equal to 0 and X is greater than 0. If 0 degrees is greater than theta S is greater than negative 90 degrees, our power factor is still going to be between 0 and 1. But this time we're going to have what's called a leading power factor because our current is leading our voltage, okay? This is true for capacitive loads, where R is greater than 0 and X is less than 0. And then lastly, we'll look at theta S is equal to negative 90 degrees, in which case, once again, our power factor is 0, and this occurs only for purely capacitive loads. So R is equal to 0 and X is negative. So whenever our power factor is 1 or 0, we do not have a leading or lagging power factor. It's not considered to be leading or lagging. Only when it has both resistance and reactance do we consider it to be a leading or lagging power factor. Okay. So we've only got 15 minutes left of class, but I want to work a quick example here. This is a different style of circuits, for lack of a better term, that you'll be asked to analyze for this last portion of the class. So this will be a pretty quick and easy one because we're limited on time here. So let's say that I have a voltage source that's supplying 480 angle 0 degrees volts RMS. And this voltage source is connected to two industrial loads. Over here on the left, we'll have load number 1. And over here on the right, this will be load number 2. Let's say that the first load absorbs 60 kilowatts at a power factor of 0.85 lagging. And load number 2 absorbs 30 kilovolt amperes at a power factor of 0.95 leading. I want us to figure out at what power factor does the source supply power? It may not seem like it, but we actually have all of the information that we need here. So let's talk about how we can find, actually, let's talk about our thought process here, which would be pretty quick, okay? So I am suggesting that the complex power supplied by my voltage source will be equal to the complex power absorbed by load number one plus the complex power absorbed by load number two. So effectively, my source is supplying power to both of those loads. So whatever power it supplies has to be equal to whatever power the loads absorb. Anybody have any beef with that? That's just the law of conservation of energy. So if I can figure out what complex power is absorbed by load one and what complex power is absorbed by load two, I can then figure out the complex power supplied by my source, okay? So let's talk about how we're going to figure out the complex power absorbed by load one. So the complex power absorbed by load number one is going to be the apparent power absorbed by load number one with an angle of theta s. It will be of that form expressed as a polar form complex number. Okay. And this theta s, let's call it theta s load one. Okay. So this begs the question, how do I find that apparent power? And how do I find that power factor angle? Well, it comes from the definition of power factor, right? If we look back up here for our mathematical definition of power factor, if I'm provided average power and power factor, I have enough information to solve for the magnitude. If I have my power factor and I can do an inverse cosine operation, I can figure out what my power factor angle is. So it looks to me like this is just going to be the average power absorbed by load one divided by the power factor for load one with an angle of the inverse cosine power factor of load one. So that would be 60 kilowatts divided by 0.85 with an angle of the inverse cosine of 0.85. And I'm just going to throw that into my calculator here. I get 70.588, angle 31.788 degrees, volt amperes as a polar form complex number, and 60 plus J 37.185 kVA, sorry, as a rectangular form complex number. Anybody have any questions, comments, or concerns about how I got from the information provided to the complex power absorbed by this particular load? I'm literally just using the mathematical definition of power factor to figure things out.
So suppose we're finding the power of the angle and not like the voltage or current, which is more than five.
So you bring up a very interesting thing here. Technically, we're not ignoring it. It's just not showing up here. So let me explain what I mean by that very specifically. So we were told that our power factor is 0.85 lagging. So our power factor angle should be a positive number, somewhere between 0 and the 90 degrees, right? Because we have a lagging power factor, theta S has to be between 0 and 90. It is. Our inverse cosine operation is always going to give us a positive angle. So what we'll see here in a moment, when we're trying to calculate the complex power absorbed by load number 2, is that we have to explicitly put a negative sign in when we do our inverse cosine operation to force that angle to be negative for a corresponding leading power factor. So very good question thing, Ashton.
Question again.
Yes. Yep. All right, so let's figure out what the complex power absorbed by load 2 is. So how do you think we're going to do it? Let me ask you a slightly different question. Because we're told that load 2 absorbs 30 kVA, what power were we given there? Apparent power. So do we need to divide that by our power factor? No, because we already have the apparent power, right? We divide real power by the power factor to get apparent power. We already have apparent power. We don't need to do that division, right? So this is just going to look like S load 2 angle theta S load 2, which is just going to be S load 2, which was given to us, with an angle of the negative inverse cosine of our power factor of load 2. And again, that negative sign right here comes from the fact that this load is operating at a leading power factor, because our calculator will always return a positive angle. We're going to force it to be negative by including that negative sign right there. So this is going to look like 30 kVA with an angle of inverse cosine 0.95. And I got 30 angle negative 18.195 degrees kVA in rectangular form, or excuse me, polar form, and 28 minus J 9.367 kVA in rectangular form. Now, I'm just going to add those two results together. So the complex power supplied by my voltage source is 92.769 angle 17.449 kVA in polar form. And finally, 88.5 plus J 27.817 kVA in rectangular form. That's wrong. I didn't store something in my calculator. Sorry, I could tell it was wrong immediately because 60 plus 28 is 88, not 88.5. So let me fix that really quickly. Oh, no. That was right. Okay, I see what the issue is. I forgot a 0.5 right here. My bad. Okay. All righty. So after all of this work, we now have enough information to determine the power factor at which our voltage source is operating. So somebody tell me how we're going to do that. Yep, cosine of the angle. Absolutely right. So the power factor at which our voltage source is supplying power is going to be just the cosine of 17.449 degrees. So cosine of the angle of what I have stored as z, or 0.954. Is this leading or lagging? Lagging. Why do you say that it's lagging? You're correct. Exactly right. So effectively, if the angle is positive, it's a lagging power factor. If the angle is negative, it's a leading power factor. Okay. All right, we have less than a minute left, so I'm going to stop talking. Okay, so what we have on the itinerary for Wednesday is to just briefly go over power factor correction. Then we have a lab. So that's next Monday. Wednesday is a review session. Thursday afternoon is your final, or Thursday evening is your final. If you have questions that you want to get sorted out, write them down. We can cover them on the review day. We might have a little bit of time on Monday to kind of do a mini review. I want to help you guys get prepared in any way that I can. So if you have questions, let's sort stuff out, okay? I did post the equation sheet on Canvas or whatever, so you can look at it and see how shitty it is. It will be provided to you, but again, I really don't think that you actually need it. So, all right, have a good weekend.